Hey folks, I thought I'd do something different this time, and I'm actually on LeetCode.com. If you don't know what LeetCode is, it's a nice way to learn how to code. They have like different types of problems you can solve, and it's basically the gold standard if you want to get into a FANG. If you do like a lot of these problems, then you'll have pretty good success in the interview process at some of those top tier companies. I'm not interviewing right now. I'm just going to do some practice problems. I haven't really done any LeetCode problems since maybe summer of 2019. So it's been about a year since I've done some LeetCodes. So I'm just going to kind of filter on the topics here. And let's go with linked list. So linked lists are kind of like my bread and butter, or used to be my bread and butter problems that I would solve. Sheesh, I'm not even in the right mindset right now to do these, but let's see. So let's start off with easy. Let's see what this looks like. So find the middle of a linked list. Oh, right. What language do I want to use? Let's do Scala. I haven't done Scala. I do Java for work, so that kind of seems like cheating. Fine, Java. Let's keep our lives simple. I'm gonna fix this editor. Actually, sorry. No, cancel. Settings, yes. Don't want 4 spaces. I want 2 spaces. Key bindings. I want to use Vim. Let's see. Xcode. Let's use, I don't like Eclipse. Solarize dark, sure, why not? Let's make our font size a little bit bigger. Let's go 16 so I don't like go blind here. All right, cool. So we got the Vim bindings, awesome. All right, so the trick with this middle of a linked list is that you have a slow runner and a fast runner. So you do like list node slow is equal to head, or actually, you know, they always have these like weird cases, like if the head is null. So like if head is equal to null, return head. And then we say list node slow is equal to head, and then list node fast is equal to head. And then basically it's like you have a while loop. So you say, I think like while fast is not equal to null, fast is equal to fast.next, and then if fast is not equal to null, then we actually do it again. So we say slow is equal to slow.next, and then fast is equal to fast.next. So basically, or sorry, fast is equal to fast.next, something like that. So basically, for every iteration on this loop, you're potentially moving slow once and then fast twice, and then you should be able to just return slow. Like that. Yeah. I can't remember if it's fast.next. Let's see. So let's think about this. So fast, well, fast is not equal to null, so we go to 1. We go to 2, is fast equal to null. We go again, so fast is at 3, slow is at 2. Then we go again, we go say fast is equal to fast.next, is fast, and then we go fast as, yeah, so that should work. Perfect. Let's clean this up, and we just run it. Awesome, then we submit. Oh, apparently I've done this in Python and it went really slow. Awesome. I wish there was a way that you could, okay, cool. All right, so linked list, sort by difficulty, so we did that one. Delete a node in the linked list. Let's see. So what are you given? Write a function, delete a node, except the tail, and a singly linked list, given only access to that node. Yeah, the trick here is just you copy the next data into the current node. So basically, if node is equal to null, we just want to return. Otherwise, I guess, yeah, so except for the tail. So that's kind of essential here. So except for the tail, so this node is never going to be the tail, which is helpful. So we can basically just say node.data or node.val is equal to node.next.val, and then node.next is equal to node.next.next, like that. Nice. Okay. Awesome. So that's moving right along here. Let's sort them by easy. Reverse a linked list. Oh yeah. So this is like one of those problems that you're kind of expected to know how to do. And you're kind of just like flipping pointers. So like you need, all right, so let's look at this. So if we want to reverse, we basically need to say, we need to say one, so like if we go from left to right here, so we basically need to say this one here, one.next is going to be null, but then you need to keep track of the like one's old next and point it at the new previous, which is, if that makes sense. So if head is equal to null, return head. And then there's like also recursive solution, but that's kind of like overkill for this one. So if you, let's see. So we need to keep track of the previous. So list. So okay. So we're gonna say list node previous is equal to null. Whoops. List node current is equal to head. And I think that's all we need to do. And then maybe list node next is equal to current.next, right? So we need to flip these. So we now need to say, all right, so while current is not equal to null, we can say current dot next is equal to previous. Previous is equal to current. Wait, yeah. So current.next is equal to previous. Then we need to set the previous equal to current. And then current is equal to next, I think. And then you just return current. I think that's how you do it. So let's run this algorithm in our head, right? So we have one. So first iteration, we're initialize previous to null, head to 1, or current to 1, next to 2, right? So current's not null. Current.next is previous. So 1.next is null. Previous is equal to 1. And then current is equal to 2, all right? Current's not null. Current.next is equal to 1. Previous is equal to current, which is 2. Current, then we got to say next is equal to current.next. Yes. Null pointer exception. I think it's like while current is not equal to null and current.next is not equal to null. So am I actually returning current here? Okay. So let's see. Man, I am rusty. So if we say, okay, so let's run through a couple of iterations of this, right? So we're just going to say the first one is, so prev is null, current is equal to 1, next is equal to 2, and then we enter that loop current.next, so 1 is going to point to null, and then previous is equal to 1, current is equal to 2, and then next is equal to current is equal to 3. All right, so something's happening here. Like, I don't think we're actually setting that connection unless it's on the next iteration of the loop, right? So it's equal to previous. So it's only printing out 5. Why is that? Is it, wait, do I just return next? Wait, that doesn't seem right. Because next is going to be null. Let's see. Yeah, that's empty. Let's see. So if current.next is null, so if current is null, that means we went ahead. Oh, maybe it's previous. That seems right. Okay, so now we basically have to just say, no, this should work if I get rid of this, right? But then it's going to give me a null pointer exception like before, right? Because next is equal to current.next. Right, so basically if next, if current is not equal to null, this is not the best way to do this, but let's see. Yeah, that's accepted, but there's a cleaner way to do this, I'm sure. I think if it's like I think you could say like while next is not equal to null, right? Because then maybe it's, oops, I want to keep that. I think I can actually do while next dot next is not equal to null. I think I can do that. No, that's not it. Maybe it is just next. And then I should be able to return current. Like that. No, I definitely can't. Okay, let's help ourselves out. So if we say if current is not equal to null, and then while current is not equal to null. Oh, and then I need to return prev. Yeah. Cool. It looks like I solved this back in September of 2019. So let's see what that looks like. Okay, so I wrote a recursive solution, and then I also wrote an iterative solution. So while head.next is not equal to null, oh, I just wrote I copied the list. I see. Interesting. Yeah. Okay. Cool. So we're back at linked lists. Reverse a linked list. Merge two sorted linked lists. Okay. So I believe that there's like, I think the way you might want to do this is like you could do some sort of recursion, right? Like typically it's not too big of a deal if they're the same. Obviously it's trivial if they're the same length, but if they're not, then it's annoying. So essentially what you can do is you can just do this recursively essentially. So you're basically going to do if L1 is equal to null, if L1 and L2 is equal to null, return null. If L1 is equal to null, return L2, and then if L2 is equal to null, return L1. All right, so that handles all of our base cases, right? And then we want to say if L1.val is less than L2.val, we want to call, we want to say L1.next is equal to merge two lists of L1.next and L2. And then we just want to return L1. Or let's say less than or equal just to save ourselves here. Else, then L2.next is equal to merge two lists of, this is merge two lists of L1, comma L2.next, like that. And we want to return L2. This won't compile. Oh, actually, it should compile, right? So how this is working, 1 and 1, they're equal, then we're saying L1.next is equal to like that. So basically, you're just merging the two lists into this one list, I guess. So let's see. Let's see what happens. Nice, look at that. You submit it. Nice, cool. Looks like the recursive solution is the right way to do that one. All right, remove duplicates from a sorted list. Okay. All right, cool. So, you know, if head is equal to null, return head. Okay, so we say int current val, or sorry, let's do it this way. So we're going to say list node current is equal to head, and then we're going to say int current val is equal to current val. So we're going to say while current is not equal to null, we're going to say actually we can just do this, while current and next current is equal to current.next. If current.val is equal to current.val, then we just call this, remember we created that delete method, so we're just going to copy over. So we're going to say current. No, that's not really the right way to do it. Actually, so what we can do is if current.next.val is equal to current.val, then we say current.next is equal to current.next.next. So we just keep skipping it. And then otherwise, else we say current val is equal to current.next.val, and then we say current is equal to current.next, like this. I feel like this is going to give me an infinite loop, but maybe not. Missing return statement. And then I think we just want to return head, like that. Whoops. Cool. Yeah. Nice. Cool. All right. Linked list cycle. All right. This is very similar to finding the middle point of a linked list. Like if you just, linked lists are super easy. Like this algorithm is identical to the find the midpoint, honestly. So it's like if head is equal to null, return head, and then list node slow is equal to head, list node fast is equal to head, and then while fast is not equal to null, and so we're going to say fast, go to fast next, and then if fast is not equal to null, and then slow is equal to slow.next, and then fast is equal to fast.next. So all right, so we're basically going through the loop and moving fast twice and moving slow once, and then at the end of this, if at some point if fast is equal to slow, return true, because that will be the cycle. And then otherwise, if we get out of this loop at any point, we just say return false. Like this. Return true. No, not return false. Sorry. Just the habit I have here of doing that. Cool. So submit. Nice. All right, moving right along. Intersection of two linked lists. Yeah, this one is weird because you have to kind of figure out the delta between the lists in terms of length. Write a program to find the node at which two intersect. I just want to make sure, notes, if the two lists have no intersection, return null. Okay. So you could go about this a couple of ways, right? So you iterate through each list. So you say while B is not equal to null, you iterate and count them, and then while A, iterate and count them, and then whatever list is smaller, you move that, or whichever list is larger, you move ahead that many points. So for example, in this case, I would move B up 1, and then while they're not equal, just increment them equally, and it'll find C1. I think that is an effective way to do it. Let's just see what that looks like. I feel like that's, so you basically end up going through the linked list twice. I'm sure there's a faster way, so let's see. All right, so if head A or head B is equal, or sorry, I wish you could do that in code, is equal to null, or head B is equal to null, return null. All right, because there will never be an intersection if one of them is null. All right. Okay. So list node current A is equal to head A. List node current B is equal to head B. And then while current A, and then we say int A is equal to 0, well, let's say 1, and then int B is equal to 1, and then while current A is not equal to null, you can just say current, so he's going to say A, actually, let's start at 0, just to make our lives easier. So we're just going to say A plus plus, and then current A is equal to current A dot next. All right, I'm going to copy that, and then we're going to change this to current B, 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 and B. Awesome. All right, so that will give us the count, and then to make our lives simple, we're just going to say if A, so we want to use A basically as our default. So actually, no, that's not really what we want to do. Yeah, so I'm just going to use A as our, like, A is always going to be the greatest one no matter what. So the way we need to do that is we say if A is less than B, then we need to swap A and B, not only the integers but also the list. So we say int temp is equal to A, and then A is equal to B, and then B is equal to temp, right? Yeah, that looks right. And then similarly, we can say list node temp A is equal to A, current A. Or no, you actually have to do head A, and then list node current A is equal to head B, and then list node current B is equal to temp A. All right, yeah, so we're just doing some swaps here. It's not really a big deal. I'll leave that space there. All right, so now A is always going to be the longer list. So what we need to do is while while A is greater than B, then we just need to say current A is equal to current A dot next, and then A minus minus. All right, so we move ahead, and then basically we say while, so presumably there could be no intersection, right? So if there's no intersection, then, okay, yeah. So basically say while A, current A is not equal to null, and current, or I think we have to do and B is not equal to null, we can then say if current A is equal to current B, return current A. Otherwise, current A is equal to current A dot next, and then current B is equal to current B dot next. Does that work? All right, so let's give an example. All right, so move ahead by 1 and then they'll meet, right? If current A equals current B. Okay. Same thing here, but here, let's see what happens. All right, so we count and then we make A the longest one, so we move ahead. Then we say if current A equals current B. So if they're both not null, then we do this. Otherwise, we return null. So at the end, we return null. I think this should work. Wait, what? Oh, I already defined this. So I don't actually need to do list node. Whoops, compiler errors. It's not a good look on an interview to have a compiler error. Nice. All right. Ooh, null pointer exception. All right, so it looks like it needs to intersect at 2 and 4. Ooh, that's not good. Have a null pointer exception. While A so I made A the longest, right? Weird. Did I swap it right? A is equal to B. Let's node temp A is equal to head A. Current A is equal to head B. No, this is okay. I don't need this line here. So I can just say current B is equal to head A. But why? So this assumes B is longer, right? Did I do anything? 0. Let's just print something out here. Let's just do A plus B. And then let's just take this test case here. Let's just throw that bad boy in there and see what happens there. 5 and 3. All right. While A is greater than B. Greater than and then system.out A. All right. Five. Current A is head B. What? Head B. Is head B null? Wait, that doesn't make any sense. System.out.println head B is equal to current A. No, that's not true. Right. So the bug is basically I'm not resetting them before. So honestly, what I should do is basically say current A is equal to head A, and then current B is equal to head B. here. And then if they're different, then swap them. So if I run this, this should pass now. Yeah. Well, that's embarrassing. Cool. Ooh, 99%. Why is it 1 mil? It's like all these while loops I have in here, isn't it? Anyway, let's keep going. These are super easy. So like palindrome of a linked list. Yeah. So again, like you're just finding the middle of the list, right? So if head is equal to null, if it's null, what do they want me to do? Return true? Like, if it's empty, is it true? You know, I don't know. Let's say false, just as an example. Could you do it in an ON time? Yeah, sure, I can do it in an ON time with a constant space. So list node slow is equal to head, and then list node fast is equal to head. Again, this is the same shit. So fast, while fast is not equal to null, and then fast is equal to fast.next. So we're just finding the middle first, and then we're going to say if fast is not equal to null, fast is equal to fast.next, and then slow is equal to slow.next, right? So this will find the midpoint. But because, let's see, so for even numbers, we really care, what we care about is, so if this is slow, they all start the same, fast, fast, slow goes up 1. Yeah, so slow will start me here. All right, so now what I need to do is basically, oh, actually, sorry, this is probably not the right algorithm for this because, So, I mean, you could use, let's see, let's think about this. So yeah, I assume that you could do this, but you actually can't. I think you actually have to like reverse the first half of the list or reverse the second half of the list. Yeah, no, that's not quite right. So if we reverse the second half of the list, what does that tell us? Yeah. Okay, so we could do it that way. So we can just create a well, that's using more space. Well, I guess, yeah, we could just swap the pointers again. So, okay, so what we're going to do is we're going to say fast is equal to slow.next. So that's going to put us here, right? And then we're going to say, and then we're going to say slow is equal to head. All right, so this is just like a reset step here. And like I mean, you could also use recursion, but that's more space. So, all right, so we need to flip this. So we've seen that algorithm. So it's like you need a list node prev is equal to null, and list node current is equal to fast, and then list node next is equal to fast or current.next. All right, and then while current is not equal to null, we're going to swap them. So I know I just did this, but I'm like going to have to remember how to do it again. So we're going to say current.next is equal to previous. All right, so yeah, so current.next is equal to previous. So that's going to be null. Previous is equal to current. Current. Next. Wait. Current is equal to next. Yes. And then if current.next is not equal to null, then we say next is equal to current.next, I think. No, yeah, if current is not equal to null here. Right? All right, cool. So then, all right, so that's going to give us 2, 1, and then current's going to not be null. So now we just need to say while prev val is equal to slow.val, prev.next, prev is equal to prev.next, and then slow is equal to slow.next. Actually, I think what I need to do is we'll say while prev. Will they ever be the same? Yeah, they will. Well, so if prev is here, we compare. Let's just do this. While prev. Oh, right, because I'm severing this connection. Yeah, so I think what I need to do, so we have fast is equal to slow.next, and then slow.next is equal to null. Right. So basically, if we sever the list here, then that's fine. Right. So then we say while prev is not equal to null and slow is not equal to null. If prev.val is not equal to slow.val, return false, and then return true. Yikes. Null pointer exception. Yay. Okay. Slow.next. Yeah. So what's the test case here? 1 and 2. All right, so fast is not equal to null, fast is equal to fast.next. If fast is not equal to null, wait. Is it fast.next is not equal to null? Yeah. Weird. Let's try it. Again, null pointer exception. Line 20. Really? So if it's fast is not equal to null and fast.next is not equal to null? Really? That doesn't sound right. But let's see. False. Expected. My input and my output was false, but the expected was what? That's weird. So wait, let's try this. Let's try this test case. So 1, 2, 1. This should be true. Yeah, weird. I don't know why that one test case. Look how many times I failed this question, and I failed it here. Input. so this needs to be true. Yeah, this is a poorly written question because it doesn't tell you how to handle base cases, but again, I got a runtime error. What the heck? Fast is not equal to null. So wait. So then there's another edge case. If fast is equal to slow, return true. Right? Because isn't that, so if fast is not equal to null, fast is, if fast is null. See, this isn't really an elegant solution because I have to throw these stupid if statements all over the place. So let's throw this one in here. Yeah. I don't think this is right. Yeah. And then I'm also getting, yeah. What did I put here? This is Java. Ew. Oh my gosh. Okay, so it looks like is palindrome if head and head.next is equal to null, return true. Head size. So I'm getting this. So this is before I knew how to get the size of a list, get the midpoint, and then is palindrome. Oh, so I'm just making this a recursive call. Ew. Yeah, I'm gonna kind of skip this one, to be honest. Hopefully you guys don't judge me too hard for that. All right. Right. All right. So palindrome, remove linked list elements. Another one. What is this? Oh, every time there's a 6. Wow. Okay. All right. So if head is equal to null, return head. All right. All right. List node current is equal to head. Oh yeah. This is a little bit of a weird case, right? So what if the first number is the number we're looking for? Then if head.val is equal to val, return head.next. Or no, it's not really a clean way to do this. All right, so we're gonna say if all right, so we're just gonna say list node current is equal to head. All right, so all right, what are our edge cases here? Because removing the element is pretty trivial. So if we want to remove the first element, then we can pull in the next one. No, that didn't make any sense. Okay, so all we're going to do is we're going to say while current not equal to null. But then, yeah, what if we want to remove the first one? Yeah, so I think the right way to do this is we pull in the value of no. So I guess the case that I'm considering here is like if there's a 6, right? Like if the val is 6 here, right? But the linked list is 6 null, right? What happens here? So if I get current and I check if current.val is equal to, so like if it's 6, right, then this is null, right? And then if I try to delete this in place and pull in the null value, then I have to do like a weird null check. But that doesn't seem like the right way to go about it. So I guess I could just say current is equal to current.next and then just return current. Oh, I think I could just do current. No. Okay, so let's think about this. Our base case is like if this is a 1 or if this is a 6, how does that break things for us? So if it's a 6, so if current.val is equal to val, then what do we want to do? We want to move to the next one, but then you're still going to be returning head, right? And then head, All right, so what do we want to do? I guess the answer is, what do we want to do when we encounter a number? Do we want to just try to skip over it as before? Or do we want to I mean, I guess what we could do, we could say, we could have this little loop. We could say while head.val is equal to val, head is equal to head.next, right? And then we say list node current is equal to head. So then we can always just return head here. So that fixes our little edge case there, right? So now when we encounter a 6, so if current.val is equal to val, then we want to say current, if current, so if we're at the end, we want next, right? So actually, so we know that this one is not it. So if we say current.next is not equal to null, if current.next.val is equal to val, and then we just say current.next is equal to current.next.next, like this. If it's equal, and then otherwise current is equal to current.next. Otherwise we just keep moving. Or do we want to move no matter what? Let's think about that, right? So no, because we still need to do that null check here. Let's run it. Yeah, okay. Let's submit that. Last expected input 1. Oh, weird. So basically, if head is equal to null, let me return null, right? And if we just put 1 in here, like this, I'm just curious. Null checks, man, and head is not equal to null, and head.val, yeah. Nice. Runtime error. Cool. All right. So those are all the linked list easies, with the exception of one of them. Odd, even, flatten, multi-level, doubly linked list, like insertion, sort, linked list, cycle 2. All right, let's do something else. Let's do We do binary trees. Let's just do tree. Trees are my jam. All right. Range sum of a binary search tree. Merge two binary trees. All right. Let's pick the first one. Yikes. Okay. Given the root of a binary search tree, return the sum of all the values between L and R, inclusive of unique values. So trees are inherently recursive, so every time I see one of these, it's like every time I see one of these, I'm just pushing for recursion, I guess. But yeah, like tree problems are like pretty much you just take yeah, okay, so you say so all you got to do is so if root.val is less than L or root.val is greater than R, return 0. What happened to my IDE not using? Yeah, okay. All right, so yeah, so if they're greater, we just want to return 0. Else, we just return root.val plus range sum BST of root.left LR and plus range sum of BST of root.right LR, like this. And then you gotta check if you gotta do some null stuff too. So you gotta say if root equals null, and you return 0. I think that should work. Ooh. 25 and it's supposed to be 32. My range is 15 and 7. So if root.val, so basically it's not catching this, wait. So if root.val is less than 7 or greater than 15, so that's going to be 10. Then we do root.left, root.right. So, all right, so 5, 30. Yeah, weird. So it's giving me 10, it's giving me 5, it's giving me 15. So it's 20. So it's giving me 10 and 15, but it's not giving me. Wait, what? 10, 15, so that's 25. So this is the right child. And the left subtree is going to be 5 and 3 and 7. Oh. Right, you can't do this, right? Because 5 is in the left subtree, but then that branches off to 3 and 7, and 7 is a part of it. So that's why I'm not picking up the 7. So yeah, I wonder if I can actually just take this out. Let me just see. But I need to do some sort of checking to see if it's less than. Right, so I can just do val, int return val is equal to So basically, we just want to check if root.val is less than or greater than or equal to L, and root.val is less than or equal to R. And if that's the case, we return root.val. Otherwise, we return 0, like this, right? And then no matter what, we just take that return val plus left and right, sums of the left and right subtree. Yeah. Ooh. And there's, yeah. This should give me 32. Yeah, this is right. Ooh, slow, which means there must be a faster solution. Although I did it faster than I did it last time. Okay. All right, difficulty, easy, merge 2 binary trees. All right, given 2 binary trees, imagine when you put one of them to cover the other, some nodes of the 2 trees overlap while others are not. You need to merge them into a new binary tree. The merge rule is that if 2 nodes overlap, the sum of those nodes add up. All right. So this new tree, I see. Weird. So it looks like you're just gonna have to traverse the tree. All right. So if T1 is equal to null and T2 is equal to null, return null. If T1 is equal to null, we return T2. If T2 is equal to null, then yeah, right, then we return T1. T1, like this. All right, so that covers the cases where there's a null, but there isn't. There's a null in one tree, but there isn't in another. Then we create a new node, I think. Yeah, I think you have to do like tree node is equal to new tree node. Right, so it gives you the default constructor, and then you say tree node dot left. Actually, tree node dot val is equal to t1 dot val plus t2 dot val, and then tree node dot left is equal to t merge trees of t1 dot left and t2 dot left, and then the same thing. Whoops. And this has to be right, and right. And then we just return tree node. All right, so does that work? The roots, so this should give me 3. Yeah, I think this looks right. And, I'm just gonna guess. Yeah, it looks right. Nice. All right. That's 2. Search in a binary search tree. All right. So the nice thing about a binary search tree is that it's kind of ordered, so it's pretty straightforward. Given the root node of a binary search tree, you define the node in the BST that the node's value equals the given value. Return the subtree rooted at that node. All right. So if root is equal to null, return null. Whoops. If root dot val is equal to val, return root. And then yeah, if root.val is less than val, then we want to go right, so we return search bst of root.right val, and then otherwise we return search bst of root.left val, comma val. Like I said, binary trees are super easy once you figure out that like they're all the same. Like every time you traverse down a tree, it's just another tree. Hence they call it a subtree. All right, like I did this once in 2018 and I didn't even need to do it again because it was just like super easy. Okay, in-array pre-order traversal. So pre-order traversal means you print first and then you visit and then you visit and then you go left, then right, then whatever. All right, so there's like a list of nodes for the children. So, oh, and it wants me to return a list. Okay, so this is like, okay. So the way you do this is you create a void method pre-order. So you overload the method and you say node root, and then you pass in the list of integers traversal like this. All right, so you just create so the way you call this is you're just going to say list integer return list is equal to new linked list integer that, and then you're just going to return pre-order a root comma return list like that. All right, so then inside of here what you're going to say is if root is equal to null, return, and then if it's not, what you're going to do is you're going to visit. So you're going to say traversal dot add root dot val, and then you're going to loop through. Am I using Java 8? I don't know. I wonder. So I can say root dot children dot stream dot for each child in, actually I think it's like this. So, geez, okay. So for each child we want to call pre-order of the child with the traversal like that. Now what I don't know is if I'm using Java 8, so this might not work, but otherwise you would just loop through them. Void cannot be, yeah, okay. Bug, and then return list like that. So you're just passing the list by reference. Yeah, so you should get that out like that. Woo! Slow, holy crap. There must be a faster way to do that. Can I do this faster instead of looping through them all? Maybe it's slow because I'm passing this in. I mean, maybe I could make it a class variable and it gets better. I'm curious. Let's just try it. List is equal to new linked list integer. Like, I would never do this at work, but it might work actually. So when you first call this, you want to list.clear like that, and then, but you still don't want to pass it around. actually, yeah, this is fine. And then have one that just returns void. If it's null, and then I don't want to do this. I just want to call pre-order again. Oh yeah, let's just call it pre-order. Pre-order. Yeah. So basically what I did is I created a second method, and I kept this linked list as a class variable, as a field, and I think this should speed it up. Maybe. No, it's not going to compile because this is list. Yeah, again. Root, and then I need to change this to capital O, like that. What the heck? And this is just list. Yeah. I wonder if this is that much faster. Yeah, not much, marginally. I wonder what the solution is to make it faster. Doesn't really matter, I guess. Difficulty. All right, so we just did in-array post order is just the same thing, but you go down the left, middle, and right subtrees before you visit or before you store the value. So I'm going to skip that. Increasing order search tree. Let's see. What's this one? Yikes. Okay. Given a binary search tree, rearrange the tree in order so that the leftmost node is now the root. Okay. So that means we start at the root and we go left and then return. So it sounds like you do like a little bit of an in-order traversal, but as you go back, so if we go all the way down the left side here, then we get a value back. So we're just going to call a helper. Okay. So all right. So I'm just going to create a helper method. So it's going to be public tree node helper. And it's going to take in a tree node root. If root is equal to null, return null. Oh, right. Because if it's null, like, that means we're, yeah. So, okay. So we get down here, we go left again, it returns back to here. Then we say, if we, all right, so we go, let's say it's 2, right? So we go here, let's say, well, that's not even a good example. So this 2's, all right, so we get back, then let's see. So if we go down, we get here, it's null, we return back, right? So that gives me 1. So that means that we just need to pass in the parent, right? That sounds right. All right, so let's see. So I think it's going to look like if root, maybe I can Command Z that, okay. So if it's null, but otherwise, wow, okay. Otherwise, root.right is equal to what we get when we go left. No, but that would imply that it's greater. That's not what we want to do. So if we traverse all the way down the left subtree, then, so if we go 5, 3, 2, 1, you'll hit null, and then you'll come back to 1. Okay. Then we have to visit. Then we have to check the right subtree. So then if we check the right subtree, dot right, no. All right, so let's say, this is an example we're trying to do here. So if we go left, we get 3, and then 3 dot right is, so yeah, okay. So so I think we need to pass in, so this is the parent. Am I thinking about that right? Maybe I don't need this. Maybe I can just use this one function. All right, so root.left, so we traverse all the way down. Then we say that, yeah, okay. So we basically say increasing BST of root.left. So we so then we just say tree node new root is equal to this, right? Now, then this new root dot right is equal to root, and then we go increasing, no, yes, increasing, so then we say root dot right is equal to increasing BST of root dot right, like that. Now, if root is equal to null, return, what do I want to return? Null. If it's null. Okay. So if it's null, I think I definitely just want to return null, but then the problem is, if we get down to 1, then we go 1 dot left, so this is null, so this will throw a null pointer exception. If new root is null, wait, so if new root is equal to null, then we want to say root.right is equal to increasing BST of root.right, and then return root. Yeah, and then if it's null, then we return the root here, so that would just return 1. And then if that's null, then we return this, right? So if it's not null, then the new root, which would be 1 dot right, would be 2. and then root.right is equal to the right subtree. So if null, then if it's null, then root.right so this is null, right? So if we're here, and so this gives me null back. If it's null, then root.right is equal to increasing BST, so that's going to be null. So then this is not correct, right? Because like if we go down the left subtree all the way to the null, then we return null, then we get back up to 1. That's this. So if this is null, then we're saying 1's right child is increasing BST of root.right, which is also null. Then we return, yes, okay, okay. And it's not null, then we get this, right, okay. Now, root.right is increasing BST to null. So if this is null, then we return root, right? Return new root. Yeah, I don't think this is right, but I'm going to try it. Did I spell it wrong? Increasing. Error found, cycle of the tree node. Yeah. This should be pretty easy, right? Because if I'm going down the left subtree, if I encounter null, I return. Then that makes the 1 the root of the tree, right? So then if that's null, then we're signaling a new root. Then we want to say root.right is increasing, or do we just want to return it? Do we just want to return it? Root.right is equal to null. If I just return it, then what happens? Then I return back up to 2, it's not null, then we say root.right is equal to root. Yeah, so this isn't right either. So if the left subtree is null, then I need the right subtree to be the new right child. But if that's null, then that's a problem. And then I return root.right if it's null. And root.right. All right, let's think about this. This is not right. So, all right, so this is not clear. Like you can see, look at that. If more than half of the people are thumbs down on this, then that's a problem. 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, maybe there's just like a way to cheat where you just like do some traversal and then you just, I don't know. All right. All right, so if we go, let's think about this. So you go down this left subtree all the way, you get to the end, and you basically need to find the case where if root.left and root.right are equal to null, right? So if root.left and root dot right are equal to null, and root dot right is equal to null, then we return root. That returns 1, right? If they're not, then we keep going left. If root dot left is equal to null, then we say root, then we just return increasing BST. No, because we need to return the root of the tree. Wait, what am I supposed to be returning? Given a binary, rearrange in order so that the leftmost node in the tree is now the root of the tree. If the left child is null, then root dot right and then we just want to return root. Okay, and then if root dot right is equal to null, well, let's do this first because we need to do, if root dot right is equal to null, then we say no, that's not, this isn't right. Curious how I did this. All right, so my submissions, looks like I did it twice. One was faster than the other. Okay, so let's see. All right, so this is commented out. So what I do is I call increasing BST. If root equals to null, return null. If we return root dot left, so we go all the way down to the left subtree. If the previous, wait, I'm using fields? How is this a solution? How is this a solution to the problem? If previous is not equal to null, yeah, I'm not gonna do this problem. Sorry I spent so much time on it. Alright, I guess I have time for one more. Invert a binary tree. Isn't this like the one problem that folks are just like, we shouldn't have to be able to do this? Alright, why not? Yeah, I remember. Yeah, Google. 90% of our engineers use the software you wrote, Homebrew, but you can't invert a binary tree on a whiteboard. Yeah, okay. Invert a binary tree. Input. So, what? Is this just swapping the left and right node? Oh, wait a second. It's a little more complicated than that. 4 seconds. So you're just swapping the left and right children of each. Are you serious? Okay. I mean, this is like a 3-line solution. So basically, if you say if root, no, always start your problems with this. whoops, return null, whoops. All right, it might be 4 lines. And then we just want to swap. So we, yeah, I think we want to swap. We want to tree node temp is equal to root.left, and root.left is equal to root.right, and then root.right is equal to root.left, or excuse me, it's going to be like 5 lines, 6 lines, 6 lines, yeah. So, and then we just want to return, so then we want to call I'm sorry, root.left is invert tree of root.right, like that. And root.left is invert tree of temp. And then we return root, like that. Yeah, wait, what? Invert tree. Yeah. Again, all the tree stuff is just recursive. That one problem before was unclear. Oh, maximum depth of a binary tree. This is a good problem too. So given a binary tree, find its maximum depth. The maximum depth is the number of nodes along the longest path. So you need to do some weirdness here where you you return, you basically have to call max depth of the left and right subtrees. So you say if root is equal to null, and then we just return 0. What the hell? Why does it do this? Okay. And then you just return 1 plus max depth of root.left, comma, oh wait. You return 1 plus the max, math.max of max depth of the left, and then max depth of the right, root.right, like that. Another 2-liner. Yeah. Okay, and all right, maybe I'll do one more, and let's end on a good one. So that we did, this one was dumb. Maximum depth binary tree, max depth univalued binary tree. I think I remember that question. All right. Given a binary tree is univalued if every node in the tree has the same value. Return true. Again. So the reason why these problems are super easy is that you just have to think about it in terms of one little subtree of a parent and a left and right child. And then you do the same thing on treating the left child as the root and then the right child as the root. And then you just return whatever you get back, right? So for example, like if I need to check if every value in a tree is the same number, then I would just do root, if root dot value, basically you'd have to say if root dot value is equal to root dot left dot value and root dot, yeah, okay. I'm not even really going to try to explain it. I can actually think of it, like I'm just going to write the code. So it's root is equal to null, return true, it needs to return true, and then we just want to return root.val is equal to root. I think you need to make sure that the left child and the right child are not null. So, yeah. Do I need to do that? I feel like I can do this in one liner. So if root is null, return true. I feel like like basically I'm trying to think if I need to do root if root.left is not equal to null, then like this is dumb. I shouldn't have to put all these if statements. Let me think before I just start writing code. If this is null, I guess I could write a helper method that takes in an integer. So a public boolean helper. Ooh. Root, and then it takes in an integer value like this, and then basically I say if root is equal to null, return true, and then if root dot val is equal to val, return true. And then I can say return root dot left, val, and root. Wow, what am I doing? Helper root dot val, root dot right, val, and helper. So basically, this is just testing the left and right subtrees. So now what I can call, I think I can call this from the root. So if I say helper, return helper of root, and then root.val, like that, I think. Yeah, I think that works. Ooh, wrong answer. That's not good. All right, so left child, let's go back to the description. So it goes 2, 2, 2. So now we go to the left child, right? Helper, call left with 2 in there. And then I call if root yeah, so bug is I actually never really checked for if it wasn't equal. So if return false, actually I don't think I actually need that one because it should just return true. Yeah. Yeah. So now, what was that submission? This one. Yikes. Oops. Run code. That should work. Yeah. Awesome. Cool. That was even faster than what? So what was my other submission? Yeah, it did some ugliness like this. Don't do this. All right. Help yourself out and make a function. Maybe I'm on a roll, so I think I might actually do one more. Let's see. Invert binary tree, univalue tree, average of levels of a binary tree. This looks weird. Invert leaf. I'll do this one. Okay, given a non-empty binary tree, return the average value of the nodes on each level of the array. So you have to do like a, what's it called? Like a level order traversal, which is just like a breadth first search. So the way that looks like, so you put everything in a queue, I think. Okay. So it's been a while since I implemented breadth first search. So let's just see what this looks like. So I think you need a queue of type tree node. Queue. See what's a new linked list. Linked list, yeah, of integer or tree node. Sorry. Yeah, so in Java, the queue is just an interface, so you need to actually provide an implementation of it. And linked list also conforms to that interface. So let's see. Now, let's on queue a, yeah, so so queue dot add, I think it's queue dot insert root. All right, so we're inserting the root, and then we're going to okay, yeah, so the way this is going to work, so we're going to say while queue dot, while the queue isn't empty, see, we have to actually we have to empty out the queue. So we have to say list tree node level is equal to new array list, like this. I guess you don't need to do that. And then while queue, not queue dot is empty, we need to say level dot add queue dot poll. Right now, we need to calculate the averages. So we have to actually say list double averages is equal to new array list, like this. And then we can say so for, all right, so we can just empty the queue first, and then what we'll say is for tree node in level, and then we need to calculate the averages. So sum double sum is equal to 0.0, and we're going to say sum plus equals node dot value, and then we're going to say queue dot insert node, like that. And then we say averages equal to averages dot add sum divided by level dot size, like this. And I don't know if I need to convert this to a double, just to be sure. And that should do it, I think. I'm not quite sure if... All right, so let's run through this just to make sure we got it right. So we put in the root non-empty. Okay, so that helps. I don't have to do anything crazy. So we put in the root, we clear out the queue. So we initialize the list, fill the list with every item in the queue. So then we add 3, divide that by 1, so this should be 3. And then we add 9 and 20 to the queue. So then we go back up, and while the queue is not empty, we create a new level, add those values. Right. So bug if yeah, so it's not insert node, it's if node.left is not equal to null, then we insert node.left, and then let's just copy this, then node.right. Like I said, I haven't implemented breadth first search in a while, but that should do it. So this should give me 9, and this should give me 20. We go back up. 9 plus 20 is 29, divided by 2 is 14.5. And then we add that. Let's run this first. I didn't return the list. Wait. And then we return averages like that. Cannot find symbol q. Maybe it's q.add. I can never really remember the API. I think it is add though. Yeah, it's add. Add. Yep. Slow. Oh my god. It's probably because I'm like doing this. Like, is there a way to get around this though? I mean, I guess I could pull yeah, I mean, it's still faster. Yeah, I don't know. I feel like I can do something like here, like this line doesn't probably need to be like that. So if we say sum is equal to node.val. So the problem that you have with trying to do it in this loop is that or does it not matter? I mean, you still need to find the sum of the level, right? So if you have 3, 9, and 20. So yeah, this is just slow because you're basically on queuing and dequeuing, which is fine, but this just seems not correct. What are some of the discussions here? I'm curious. Level order traversal. Yeah, it's just ugly. Python 3. Append root. Node self.pop 0. If node is none, not none, node.left. Yeah, I'm sorry. I'm just gonna have to look for a Java solution because I don't wanna. All right, you put in a queue, q.add while queue is not empty. return count is q dot size. Oh, yeah, just keep track of the queue size before you start. Yeah, and then you pull that same number, and then you can just add them in the one loop. Nice. Nice, nice, nice. Nice, so then this is O of n. Very cool. Okay. Awesome. All right, well, yeah, I just did some LeetCodes for a few hours here. I hope you guys kind of enjoyed it. If you have any questions or if I went too fast or anything like that, just let me know. And if you like the video, I can do more of these. It's always good for me to brush up on my data structures and algorithm skills. But yeah, hope you enjoyed it.